I'm Josh Ware, and I'll be giving our Week 9 presentation on behalf of the Ivory Team, as you see listed here. Some stuff we're going to go over today. We're going to review some old stuff from our old system. We're going to introduce our new system. We're going to look at the frequency response experiments, the modeling of the FOPDT approach. We're going to compare some results. We're going to show our experimental Bode plot. We're going to show our model Bode plots, and we're going to compare some more results. Then we're going to wrap things up with some fun conclusions. So our old system, we were originally on the duct cooling system where the input was in percent, and it was the blower motor. I'm sure we've heard this 3 times already now. We'll keep it short. It controlled the output, temperatures, degrees Celsius. It is inversely proportional, as we'll see here in a second. In our experiment, both dampers were open. This is our steady-state operating curve. Again, you can see that ours is declining because as an increase in percent, we do have a decrease in temperature. You see roughly our output is about 0.35 times the input. Here's an example of our step-up results. As you can see, it's both the model and our experimental data. As you can see, which was talked about in our previous presentation, our data actually follow the model pretty extensively. Example of our step down, again, which actually had better results in modeling our experimental data in the step down than we did as a step up. There was more confusion in our results in the step up. Our new system, the fun system, thank you, Dr. Henry, for being so kind as to introduce a new system for us. We're on the absorber water flow system. Things are getting kind of hectic on the other system. In this system, the input is the motor speed in a percentage, and it controls the output, which is the flow in pounds per minute. Some important information has been given to us, which we'll see here shortly, like this one. This guy is a step response that we were graciously given. As you can see here on the down, we stepped down to 40%. We were given about 4.5 pounds per minute. And on the step up, we're going up to about 80%, and we're getting about 13 pounds per minute. We're also given some fun data. Here the output versus input. So will help us calculate our amplitude ratio, which we'll need in our frequency experiment. But some important information about our system. We were given a gain of 0.21, dead time of 2, and a time constant of 2. This will be crucial when we start doing the modeling and doing our experiments to find what frequency we need to start at. So let's talk about some frequency. To start, we need to find a couple parameters here. We need to find omega here by our given data of our time constant and converting it into frequency. And then to find the amount of time we need to run, we took 6 times the time constant, add some time to it because it needs to be longer than that, plus the time it takes to make one cycle, which you can see in the bottom equation here. This is graciously given to us, information on how we can find, important information we can find when running the frequency experiment. We can find the change in output and the change in input, which we'll see will help us be our amplitude ratio. We can also see that the time it takes to make one complete cycle in the input T and the lag behind it, little t here, will help us. They're important parameters will help us later. To find the amplitude ratio, we go back to that last graph. We see it's delta M or delta C over delta M, or just the slope of the SSOC curve or graph. In the phase shift, we see those, like I said, those times were important. The lag time over the time of one cycle times 360. Then with all that, we can actually graph all of our frequencies at different times. We actually graphed about 10, halving the frequency and doubling the frequency every time. The things that we can get from this would be the gain, the KCU, the order, and the ultimate frequency. As was talked about earlier, so I won't bore you to death. The gain is at the asymptotic value, and we can find at negative 180 degrees, we can find the ultimate frequency, which helps us find the controller gain. To model it, we use some equations that were given to us for the input and the output, adjusted with our baselines, which is not shown in here. And then to model the amplitude ratio and the phase angle, we can use these the bottom two equations. And as you can see, we did adjust it for our input and output baselines. So here's an example of one of our frequency experiments. You can see here how we calculated the delta M and delta C, as well as the time it takes in the to make one complete cycle, and to make or between amplitudes, and to make the lag here. Here's an example of our Bode plot. From ours, we got a gain of about 0.19, and coincidentally, our ultimate frequency of also 0.19, which helped us get our KCU of 1 over 0.07, which is a quite large number. Some parameters we gained, just to tabulate it. You see our gain was at 0.19. The order of our system was just about 2. The ultimate frequency of 0.19. Our gain of 1 over 0.07. Time constant of 1.1, and a dead time that's actually 4. I don't know what happened there. I think my dog might have touched it when I was typing it, but it's actually about 4.1 seconds of dead time. Then we modeled it, as we talked about previously, with those 4 equations that we showed a few slides ago in Excel. You can see that when we talk about the frequency, the top graph here, a lot of our data follows it very significantly. There's not much deviation whatsoever. And so we look at the bottom graph. We see in the higher frequencies that we do get a lot of deviations, a lot of error, or not really error, but uncertainty. And that's because we are at a higher frequency. But, I mean, overall, we are following the same trends. To kind of tabulate some more comparisons between the amplitude ratio and the phase angle, you see here we did our experimental, which would be the left of the 2 columns, and the right of the 2 columns would be the modeling data we use at each frequency. And then you can see there's not much difference except for in the phase angle towards the end. There's some noise going on. Some awesome system conclusions. Our new system is amazing. It's a lot less bogged down. And the best estimate of our FOPDT is our gains about 0.19, our KCU is 1 over 0.07, our time constant of 1.1, and a dead time of 4.1. All right, so